Okay, good morning. Apologize for the last week that skipped a lesson, but I hope you managed to take advantage of the lectures. So if you remember, 2 weeks ago we're still talking about the problem of estimation, where we have a parameter space. We generate a sample according to some parametric distribution, which I also called the channel or the noisy channel from the parameter space to the samples, and we usually think about these as IID samples, which means that they are sampled independently, which means that the likelihood of the data or the probability of the data given the parameters is simply a product. And we said that we usually move this sample to some functions of the samples, which I usually denoted by an empty square bracket, but now we are going to fill it in, which we call the statistics of the sample, like the sample mean or the sample variance or many other functions of the sample. And from that, we usually generate something which we call the estimator of the parameter. So it's supposed to be a function of the sample. So this is the estimation problem. And we talked about many possible good candidates for estimators. In particular, we talked about the maximum likelihood estimator, which was simply what? The value of the parameter that maximizes the probability of the data. So when you think about this as a function of theta, conditioned on given the samples, but not a probability distribution, but so this is what we call the likelihood function when we think about it as a function of the data. So this is the likelihood. And maximum likelihood is simply the thing that maximizes the likelihood. Okay, as we said, it's not unique, but it has some it's generally not necessarily unique, and it has some very good properties like consistency, when n goes to infinity, if indeed the sample was taken from this distributional form, then we know that in the limit of very large sample in probability, the estimator is going to approach the parameter. It's not only approaching the parameter, the probability density function of the estimator given the sample. Sorry. So this probability density function is actually approaching in the limit a normal distribution with variance, which is the best we can achieve, which is precisely. So if it's unbiased, it's approaching in the limit. Even if it is biased, a normal distribution where the mean is the value of the parameter and the variance is simply 1 over n the Fisher information, which means that in the limit, the maximum likelihood estimator is not only consistent, it's also efficient in the sense that it achieves the minimum possible variance among all estimators. Okay? So this is just to remind you what we're talking about. And we now want to discuss a completely different topic, which I mentioned briefly in the last lesson 2 weeks ago. And this is something about the properties of these functions that are functions of the sample that we call good statistics or sufficient statistics. And in order to do this in a good way, I'm actually going to introduce today, to extend some information theoretic measures that we introduced already, the cross entropy, for example, that appears in the sequential decision problem, and extend it to other functions that some of you, of course, know already, the entropy function, the conditional entropy, and the mutual information, which at this point I'm only going to introduce, and only later on we're going to find the really important properties of these functions, which means the coding theorems, data compression, and error correction, but this will come later. But already at this point, I mean, when we talk about classical statistics, information measures are going to become more and more important. And actually, so this is completely unstandard what I'm going to do now. I'm going to mix information theory with classical statistics in a way which I think is much more appropriate and much more useful for many of you who are not going to do communication theory. And only later we'll discover how important these functions are for other things. But I just want to make sure that all of you are with me on these topics. I mean, efficiency, consistency, and these important properties of maximum likelihood estimates. You all know what I'm talking about. Okay. So we said that there is some functions of the samples in general can be high dimensional functions here, which are, in a sense, and we saw it already when we calculated the maximum likelihood estimate of a Gaussian, for example, or the mean of a Gaussian, or the parameter of an exponential family, or Poisson, or you did many other exercises. You saw that there are some functions, usually the sample mean, or the sample second moment, or the sample whatever, some other crazy functions of the sample, which in some sense are sufficient, in a sense which I'm going to define more appropriately now. I just want to remind you of one thing. I mean, so essentially we denoted these functions as so there was another notion that I mentioned already. So the variance, of course, and the biasness of the estimator, which are, as I said, important but not that important. We also show, of course, the Cramer-Rao in several forms. I mean, so the variance of an estimator is always bounded by, for IID sample, for the Fisher information. We saw that the Fisher information has all sorts of nice properties which are related to the Hessian matrix of the likelihood at the maximum likelihood point, which are related, which are in general related to the second derivative of the Hessian matrix and related to other forms here. But there's one more thing I wanted to mention before going to the notion of sufficient statistics, which I just wanted to make sure that I say it. Yeah, okay, so we saw that efficient estimators, so this was the Cramer-Rao bound, and we saw that equality in the Cramer-Rao bound appears when? For which type of distribution, and what type of distributions can achieve the lower bound here on the variance in general, I mean, for any n. I just want to make sure that you remember that. So when did we achieve an equality here? So efficient estimators are precisely those that have the minimum variance, and if they're unbiased. You proved, I hope you proved that you can slightly generalize it to biased estimators, and you get the derivative of the bias as part of the bound. I hope you noticed there that the derivative of the bias can be very large. In some cases, it can be so it's actually for very small derivative of the bias, the bound can be meaningless. I mean, it can actually tell you something which has no meaning whatsoever, like the variance is positive. But if you have high sensitivity, then actually this bound can be very important. And there are many applications of this generalized Cramer-Rao bound to the case of biased estimators, which are actually very useful, and are used in neuroscience now very often. So again, for the computational neuroscience people here, this is actually useful. But again, efficient estimators, when do we achieve an equality here? Do you remember? Just want to make sure that there is some continuity from here to 2 weeks ago. So when was it? What was it? What was this Cramer-Rao bound, by the way, for you who know some physics, is very similar to the uncertainty principle in quantum mechanics, and some of you may notice it. It's actually telling me that the product of two variances is always greater than some number, 1 in this case. And indeed, there is a deep relationship between Cramer-Rao bound and the uncertainty principle in quantum mechanics. In some sense, it's telling you, okay, you cannot specify the parameter too well from a finite sample. There's always some uncertainty which is determined by this Fisher information. And the Fisher information is some sort of a complementary of the derivative of the log of the probability. The sector parameter is a variable that tells you something about possible uncertainty. So actually, those of you who really like this connection with physics, I know there's a few here who may want to see it, actually, you can really take it a lot further and really show that the Cramer-Rao bound is a form of uncertainty relation. Actually, all the uncertainty relations in quantum mechanics are some sort of Cramer-Rao bounds. It's a probability. It's a probability of estimation, so I cannot be too good. And the shifted Cramer-Rao bound actually also has some interesting implications in quantum mechanics. But this is again just an aside. So efficient estimators are precisely those for which this bound is achieved, and we saw that in this case we could see that the log probability is of what we call the exponential form, which means it has the form of some function of the parameters multiplied by some function of the data, plus possibly another function of the data and another function of the parameter. So these distributions for which the log, and this can be in general a multidimensional function, these are called exponential forms, exponential distributions, and they're very special and very important for everything that we do in statistics. We saw that the normal distribution, the Poisson distribution, the chi-square distribution, all the distributions you like, exponential ones are all, the nice ones are usually of this form, and the log of them has this particular factorization property. Yes?
So the bound is saturated. There's two conditions. There's a condition on the estimator, it's the maximum likelihood, and the distribution.
So there is it's a good question. I mean, so in order to saturate the bound, we actually first assume that theta hat is an unbiased estimator, which in this case means that this A, which was theta hat in our derivation, is actually an unbiased estimator. But I can ask it without assuming this. When can I get an equality here? And I see that in general I get an equality here if and only if I have an exponential form. So even without assuming unbiased estimators, which, as I said already, is some sort of a weak property because unbiasedness is not invariant with respect to parameter change. But we would like to have something which is more flexible. And actually, this parametric distribution is invariant under parameter change. I can now take any transformation of my parameters. It will still stay an exponential form, although it's not always obvious.
So just the exponential form is a sufficient condition?
So the exponential form is sufficient condition for the fact that the variance achieves the minimum, even if it's unbiased only for one representation. If there exists a parameterization for which this estimator is unbiased, and now I take any transformation of this, I may lose the unbiasedness, but I may not lose the exponential form. So exponential forms are much more robust in that sense than the properties of unbiasedness. Anyway, so we'll come back to this exponential forms later on today, and we'll see that they have also this very important property of what we call sufficiency. So that's why I want to start now. So I want to call T of x, so this is the definition. So T of xn some function or a general vector function of my sample is called sufficient statistic for the parameter for theta in the family px given theta, if and only if this is the definition, yes, the probability of the samples given the statistics and theta is independent of theta. It's not going to change if I only condition it on the statistic. Okay? Yes?
T has dimension the same as the number of parameters?
So T usually, I mean, it's not part of definition. But it's a vector. It usually has the same dimensionality as the parameters. But as I said, parameters can be funny. I mean, you can have some dependencies between parameters. And in that case, you may have less statistics than parameters. Or you may have, so without saying more, which is something which I'll define in a second, which is called the minimal sufficient statistic, I can't say that in general. So of course, there are trivial statistics. So this is my definition of sufficient statistic. And trivial example is just Txn equals Xn. So in this case, there's always a sufficient statistic. So this is by itself, of course, is not interesting. I didn't say anything here. But so it becomes interesting only if somehow you manage to compress the data. You really have to describe it in a function which is independent of n, or at least weakly dependent on n. We'll see later on when we start talking about learning theory that it may have weak dependence on n, like log n, or even some sublinear function of n, and still be good enough for many things, as long as it's not linear in n. Okay, so this is just to show you that there are always sufficient statistics, but we actually want something more than that. And it's easy to see if you're Bayesian, then if there is a prior over theta, then this is equivalent to say that the probability of the parameter given the sample and the statistics, which is actually, of course, redundant here, it is a function, the probability of the sample and statistic is a function of is the same as the probability of the parameter given the statistics only. Which means actually anything that I can know about the parameter depends only on the value of the statistics, nothing else in the sample methods. So this is just Bayes. I leave it to you to show. Okay? So essentially, this may give you a better intuition of what we mean. Why is it sufficient? Sufficient because everything that the sample can tell us about the parameter is captured by this function, the statistic of the sample. So let's just look at a simple example, but non-trivial. So consider coin flips again. So in coin flips, let's say that I have n coin flips. So you know that the probability of getting m successes is what? Is n over m, theta to the m, 1 minus theta to the n minus m, where theta is the parameter between 0 and 1. Okay? So this is the binomial distribution. So what is a sufficient statistic for theta in this case? So given a sample, given, let's say, n coin flips. So the sum, or if I think about them as 0, 1, I don't have to. But, so if it's 0, 1, then the sum of xi which is precisely the number of successes in this case, M, is a sufficient statistic. Okay, why is it sufficient statistic? Because all the samples that have the same M have exactly the same probability of theta. So once I know this, there's nothing else in the sample that can actually tell me anything about theta. Okay? So you can easily prove it. Prove this, for example. The probability of theta given the sample is just the probability of it's completely captured by M. Okay? Okay, sorry. In this case, if you want in first definition, the probability of the sample in this case, given the statistics, this is my statistics in this case, is just 1 over n over k, n over n, which is n over the value of the statistics. So in this case, it's independent of theta. Independent of theta, which means everything that I know about the parameter is captured by this. So this is a very simple example. And of course, you saw it, you show other examples. So what is really so important about it, why I think that this is a fundamental quantity, property of distributions, is that in some sense it captures something intuitive, which we call the relevance, or the relevant information in the sample. That's the only thing we really need to know. The sample is very noisy. The n factorial perturbation of the samples, there are many, many samples. All of them are summarized. All the information that I care about is summarized by this quantity. So this is the notion of sufficiency. This is very important. But of course, as I said, we would like to have something more than that. We want to have the simplest possible statistic in some sense, because otherwise we can have trivial statistics, which are like the sample itself. So in order to characterize it, we first prove a very simple theorem called the Neyman-Pearson, the Neyman-Fisher-Neyman. Neyman and Fisher. It's again very, very old, something like 1922. Factorization lemma. So T of xn is sufficient for theta if and only if what? The probability of the sample given the data can be written as a product of two functions. One of them is a function of the sample only, and another one is a function of the parameter and the statistics. So if and only if there exist functions h and g such that. Okay, let's try to show this. This is not so hard. Okay, so let's assume first that there is a factorization. Okay, so I can actually write a distribution like this, and I want to show that the probability of the samples given the statistics and the parameter depends on independent of the parameter. Okay, so how do I do that? So the probability. So again, this there's some insight here which is really important. So essentially, given the statistic, the sample space, the n-dimensional sample space, is actually partitioned into regions for which the statistic has a certain value. So any statistic induces a partition of xn into regions. Let's call each one of them, let's say A of t is going to be all the samples such that t of xn equals t, some value. So again, it's in general multidimensional in two cases. Okay, so for all the samples for which this has a certain value is some partition. Okay, so I can think pictorially about it. If this is my space of all my samples, so I may have regions here. Here t equal t1, here t equal t2, and so on. Actually, in general, this is a continuous function. Think about all the samples and all the means of the samples. So, of course, it's some sort of projection. All the samples have the same mean. We lie on one part like this. Okay. So it's a huge compression. So in some sense, what we are going to talk about is what we call a sufficient partition of the sample space. I mean, so what is any statistics inducing such a partition of the sample space? And of course, you can always have this is an exhaustive partition. I mean, the sample space itself is the union over all the t's of this A of t's. Okay, and there are, of course, this joint of t prime is a null set if t is different from t prime. Okay, these are functions. Okay, so there's some sort of equivalence between a sufficient statistic and a sufficient a partition, or any statistic is a partition of my sample space. Okay, so so now I can just I'm going backward. So I just want to prove this. So essentially, if we have the factorization, the probability. So this is the proof of the lemma. If the probability of the sample being some particular sample, yeah. Okay, so what I mean by this again is this is the random variable. This is a particular realization of the random variable, given the statistics of this realization, which equals to some value t, to make it small. So this is a particular value, and the parameter is what? So I can write it using that's the definition of conditional distribution. This is the probability of the sample being some particular value given theta, divided by the probability of t of xn equals some value given theta. But now I simply use my factorization lemma. So this is by the factorization property is this function of xn times this g of the statistics and theta. And this is simply this is the sum over all the samples in this A of t. What is the probability of a sample being in this set? The sum of all this. Now, so this is the sum of all possible. This is of all possible samples that achieve this value of the statistic of the same thing. The age of xn, not h prime of n if you want, plus g xn, t of xn and theta. Okay, but now you see immediately that this is independent of the sample. It depends only on t, which has the same value for all of them, so I can take it out of the sum. So this equals age of xn divided by, multiplied by g, this g of t and theta. And here it's the same t and theta, so I can take it out of the sum, because all those samples have the same value of t. So it's independent of those samples, divided by the sum over all the xn prime belong to ht, the A of t, that's what I should write here, of this age of x prime of n. Okay, I know it looks a little funny, but then this g cancels, and I get something which is independent of theta. Okay, so that's it. It's very simple. So essentially, so I show that if indeed the factorization is true, then you can simply take the part that depends on theta only outside of this Bayes rule, and you get a ratio of two functions. One of them depends on the sample only, and one of them is normalizing it among all the functions, all the samples that have the same value of the statistic in this partition. But this is independent of theta. Okay, the other direction is even simpler. If it is sufficient statistic, then I can simply write, using Bayes rule, define G to be the conditional function of P given theta, and I get the factorization. So the other direction is simple. I leave it to you. This is the harder part. The reason I wanted to show it, so this is essentially showing that the name of factorization is really an if and only if condition. Any questions about it? May look a little strange, but there's nothing here. So now I can define something which I want to call the minimal sufficient statistic. So this part of the board is essentially useless. I'll start here. So I want actually the simplest possible partition of my sample space. So I'll call Sx. The sum is in, this distribution, what is the probability of the statistic getting a certain value? It's the sum over all different samples for which the statistic has a certain value t. Okay? Because all these samples are different. So essentially, I just write this as a sum over all the instances for which this is true, which means all the samples in this set, I define this set to be the samples for which the statistic has the value t. So this is a collection of samples. Okay? For example, all the samples of 10 Gaussian variables that have exactly the mean 1. So there are many, many samples like this. In general, it's an integral, not a sum, of all possible values of 10 samples that have the mean 1. Okay? So think about this not as a sum, as an integral, but I just, for simplicity, as usual, write it as a sum. If it's a discrete variable, it's a sum. And so I simply write this as a sum over all those that have a certain value. And here I plugged again my assumption about the factorization. And then magically this function of the statistic and theta disappears. Yes? Which one? Here.
You need to write that xn is xn and t shall xn is t, no?
Yeah, that's what I did, no? So t shall xn is t, and I just wrote it. This was my definition of sufficiency. No, I mean this is always true. I mean I can condition this on theta, but I want to show, in order to prove sufficiency, that this particular distribution is independent of theta. This was my definition of sufficient statistic, and that's what I did. In order to show this, I simply wrote this using Bayes rule as this conditioning. And I mean, this is just definition of conditional distribution. I condition it on this. So I divide it by the probability of this. Everything is conditional on theta. And then I got rid of the dependence on theta due to the factorization. Okay, so for essentially, we want to say that f of xn is called a minimal sufficient statistic. Shortening. If what is the intuition here? So I want somehow the coarser description. I want, if for any other, let's say, if for any other sufficient statistic t of xn, if t of x had one sample is equal to t of x2, this implies the S of x1n is also equal. So this is a funny way of saying it, essentially telling me that any partition by any sufficient statistic is a subset of a partition is a subpartition. It's at most a subpartition of the minimal one. So the minimal one in this language is the coarser partitioning of my space, which means that if there is another sufficient statistic for which these two things are equal, then they must be equal also for the minimal sufficient statistic. Another way of saying it is that there is a Markov chain. So if from xn I calculate T of xn, so for any other sufficient statistic I can calculate it by, so Sxn is always a function of any other statistic. So if you give me the value of T, I will merge them if there exists any sufficient statistic for which these two things are equal. So all the samples for which there exists a sufficient statistics which gives me the same value, it will induce the same value of S. So if you want to be a little more fancy mathematically, this is the coarser partition of my space which is still sufficient. It's the infimum over all possible partitions. Whenever I can unify them, I unify them. Okay? So this is the simplest possible partition of my space. Yeah. If you want, any other sufficient statistic is a refinement of a minimal sufficient statistic. Another way of saying refinement means that there exists some partitioning of the sampling space with the minimal one that I split into two, for example. So in that sense, the minimal sufficient statistic it seems like in some sense the simplest possible one, and so this is a Markov chain. And what we mean by Markov chain, I mean so for any sufficient statistic, S is simpler than T. Which means given T, I also know S. Well, no, given T, S is independent of X, but whatever. This is a Markov chain. You already saw what a Markov chain is, okay? All right. So we'll come back to this later on. I'm going to, in the second hour, I'm going to define a few more functions, information theoretic functions, which will allow me to make this even more precise. But there are several other important properties of sufficient statistics. Some of them are somewhat tedious to prove here. Which so without the lemma factorization lemma, you can actually take it as a definition if you want, since it's an if and only if condition. And for many ways, it's enough to show the lemma factorization. If there is this sort of factorization, to actually argue that something is a sufficient statistic. So I can here, for example, generalize or at least prove for now more precisely the statement I already said, if you remember, in the context of sequential decision. We actually said there, so there's a simple example that I now can prove in sequential decision in Bayesian decision theory. We said that the likelihood ratio, L likelihood ratio of xn, which was what? The probability of the sample in one state of the world divided by the probability of the sample in another state of the world. I said before that this is sufficient statistics for the choice of the world. So essentially what I want to show here is actually, it's even a minimum sufficient statistic, but let's say that we want to prove it now. So how would you prove it? This is actually something I asked Noga to ask you to do at home. But so you just need use the factorization lemma and show that you can actually factorize the likelihood, the probability, and actually I showed it to you already, just if you remember. So for example, I showed you that the probability of omega given the sample can be written as some sort of a sigmoid function you remember, like a perceptron, where what appears in the sigmoid function are only the likelihood ratios. So in this particular case of binary decision, the likelihood ratio is actually a minimal sufficient statistic for the state of the world, omega. So this was some function, let's write it like this. This was actually, could be written as a function h of x times g, which depends only on omega and the likelihood ratio. So if I can do this, if I can show this, I actually proved that my, I don't do it in the right way. If this likelihood can be written like this, and this, of course, a likelihood ratio and omega, then the likelihood ratio is indeed sufficient statistics. So I just use the Neyman factorization to show it. Okay, so this is something you will show at home. So now so this was the state of the understanding of what sufficient statistics means. I mean, Fisher introduced this in 1922. As you may know, Fisher was not a mathematician, although he really founded what we call modern statistics. He was actually a botanics. I mean, he was he developed all of statistics in order to classify plants. But so he had this very strong intuition that this notion of sufficiency is very important. And then, of course, with Neyman, he actually proved this nice theorem. And it stayed like this for about 20 years until something like 1940, when it was actually shown by three mathematicians, Pitman, Koopman, and Dormois, independently, for different cases, more or less. The first one proved it only for discrete variables, and then the other one generalized it. So essentially, they proved that the only distributions for which there exist sufficient statistics are what do you think? Exponential forms, yeah. So there is something very disappointing. There was something very disappointing about this theorem. So let me write it here. I must say that this was the state of, this was essentially the killer of the importance of the sufficient statistic for a while. So everybody knew that for anything practical, the sufficient statistics are very important. And actually, before I show you the Pitman-Koopman-Dormois theorem, just one simple property. So some proposition, if you want. The maximum likelihood estimate, if it exists, of theta is a function of the minimal sufficient statistics of T of xn if T of xn is actually a minimal is a sufficient statistic. You don't even need the minimality here. I'll write it. So why is this true? Again, coming from the actually it's true both for the maximum likelihood and the maximum posteriori. Actually, it's also true for the conditional mean. So why is this true? So the proof is really simple. So theta maximum likelihood is the argmax of the log likelihood, for example, okay, of log of p of xn given theta. We said that the log doesn't change anything here, but this log. Now I use the factorization lemma. So this is the argmax of log h of x plus log g of theta and t. Okay, this was my general property. Okay, this is Neyman factorization. But of course, this is independent of theta. So this is simply the argmax of the second function of log g of theta and t. And this already forgot the sample. The only thing which it depends on is, so whatever it is, I mean, take the derivative and solve it, it's going to depend on the sample only through t. Okay? So this is it. So you see that whenever there exists a sufficient statistic, the estimators, all the estimators, the maximum posteriori, it's exactly the same argument. For the conditional mean, you have to work a little harder, but it's also true. So if there exists sufficient statistics, all the estimators depend on them. Okay. So this is, you see why it proves it? Yeah. All right. So now I want to just state these two theorems. One of them, so there are many good things you can do with sufficient statistics. So as I said, the disappointing fact is this theorem that I'm just going to state. I'm not going to prove, because I'm going to actually use something much more interesting later on when we talk about entropy and maximum entropy. But so the theorem, which is called PKD, or Pittman, Koopman, Domar. If you want the exact spelling of the names, look at the notes. PKD is that essentially Px theta, any parametric form, has sufficient statistics which are continuous functions of the both sample and has sufficient statistic which are continuous and differentiable actually. And this is actually a very strong assumption. Differentiable functions of the sample. Now, of course, when I say that, I actually mean I already assume that x is a continuous variable and I can actually take derivatives. So, but it's not really important. This is precisely the differences between these different versions of the theorems. The first proof was actually assuming that x is the differential, that I can actually take the derivative of dp to dx. And then later on it was shown that it's not really necessary. So in general it's true, but if it's differential functions, then if and only if, again, log p of x given theta is of the famous exponential form. Some function of theta, some other function of x, plus, which, as I said, can be in general multidimensional. And usually the dimensionality here is the dimension of the parameter space as well, plus some other function of x plus some other function of theta. Sorry, this was theta and this was x. Okay? Which means p of x at theta is of exponential. Okay. So this is the theorem. One direction is trivial. I mean, if it's exponential form, then the Neyman factorization is correct. And then we can actually see what the statistics are. So let's just prove that if this is true, exponential form implies Neyman. Okay, why is it true? Neyman's factorization. Why is it true? And what are the statistics in this case? So you just write it. P of xn, again, I assume here IAD. So it's just the product. Which is just the exponent of what? Of b theta times sum of a xi plus c of theta plus n times c of theta plus, again, this sum here. Okay? I just took the product and summed in the exponent. Okay? But what you see here, that this is simply factorized into exponent of this sum, which is exactly what I want to call age of xn, times a function which depends on theta and sample only through these things. So we can call this exponent e of b theta times these functions plus c of theta plus n c of theta. This is just g of theta and t equal these sums. So we see from here not only that factorization exists, but we also see that the statistic is additive. I mean, it's just a sum of those functions over. So these are the sufficient statistics in this case. Now, when they will be minimal, if and only if these are linearly independent functions or functionally independent functions. I mean, I cannot express these numbers with any smaller set of functions. Okay. So, but of course, I can rotate my parameters and so on. So, by the way, you'll see in the literature that for exponential forms, we really like to move to a new set of parameters where these are just the parameters. These are called the natural parameters of distribution. And they have all sorts of nice properties. And we also know that they're efficient. So we can get efficient estimators. And unbiased estimators, if we make them unbiased, are all going to be functions of these sufficient statistics. Okay, so this is actually very nice because for exponential forms, not only we have sufficient statistics, these statistics can be added, can be calculated one by one. I mean, I give you one example after one sample after the other. All you have to do is to add them to my memory. Okay. Now the other direction is a little more tricky. I need to use all these analytic properties. I need to take derivatives and integrate and so on. So we have the proof, almost the proof in the book. It usually takes too long, so I want to stop here. Okay, so we'll take a break. And the next hour is actually very important because I'm going to introduce information theoretic functions, especially the entropy, the emission information, and to prove some other properties of the KL divergence we didn't prove so far. And then at the end, I hope to characterize sufficient statistics, really justify this term that sufficient statistics capture the relevant information about the state of the world or my parameters using the definition of mutual information. So don't go away. Stay with us for 10 minutes of commercial.
מה זה PEC? כן, אבל במטלב באלף פשוט שזה הסוג המיוחד הזה של הסיבוב. זה לא כמה זה לא משלם, כי יש לך אני אומר שזה לא... אז מה יש לנו? שזה ארגון שלהם, זה לקח את זה, להכפיל את הפרעה שלו, להכפיל את הקרוס הזה ולהכפיל את האנשור. כן, אפילו השתמשתי בזה בעבר, והאמת, סתם תמיד אומר, כשתגיע למשהו שהוא לא, אתה יודע, אפילו לא... כן? אבל אפשר לשאול את זה. תגיד, תביא את השאלה לא, אבל אין זה לא נכון, זה לא הפונקציה הזאת. הנקודה. תוסיף את הנקודה 11, זהו. זה לא כל הדבר הזה. כי אלפא, כי אלפא לא... אלפא הוא אפס. במקרה הזה אלפא הוא אפס. במקרה שכאילו שיש לך סופר הפרדה מצוינת, אין לך אלפא הוא אפס, בבית הוא אפס. אתה יכול לעשות דברים אחרים. הנקודה זה כל מה שיש. אתה יכול לקבל, אתה מכיר את המאמר הזה? כן.
כן, יש כבר אחוזי הכללות של ה...
זהו, אז אני רוצה לשמח איתך.
כן,
אני רוצה לשמח אותך. העניין של ההתפוצצות על הדיאגרמה הזאת, אתה יכול. האנטרופיה או זה נכון,
יש לזה תומות של הדיאגרמה הזאת היא בעצם באה עם התמרים מהתרבות, אתה לוקח חשבון זה יכול להיות גם
אם אני אתן איזה סף שהוא...
אבל זה גם מעניין נכונים, ההגדרה הרגילה של אינפורמציה זה בזום אחד אינפורמציה זה יכולה לגמרי. לכן זה acquisition, זה acquisition information והדבר הזה
אני חושב שיותר טבעי להגדיר acquisition information סכום של היחידים ופחות זה יותר טבעי.
זה מה שרוב האנשים עושים. זה כל הדברים האלה דבר נשמע. השאלה היא למה זה טוב. השאלה היא מה אתה עושה.
לא, אני חושב לו קצת פרוספרשן.
יש אינפורמיישן זה הגדרה. אתה יכול להתווכח על הגדרות כמה אתה רוצה, זה לא יכול להתווכח. השאלה היא מה המשקפים שלהם אפילו. לא, מה הכי מועיל. אחרי מה אתה יודע להראות על מודיעין. מוטי אינפורמיישן בצורך כלל.
אני לפחות הרבה מאוד
ושם זה באמת מוצדק אם אתה משתמש בתכונות האסימפטוטיות, המולטי-אפליקליות שלנו. למה אתה צריך מולטי-אפליקליות של אינפורמיישן? זה לא סתם להתחשק לי להגדיר.
אני לא יודע, אני נכנסתי רק
אתה עושה את זה כי זה מועיל למשהו. זאת אומרת, מבין משפטי הקידוד כל ההגדרות האלה.
השיעור הוא עד רבע זה?
כן, זה לא חייב. לא יכול להיות. קשורים ביניהם כמובן. הפרמטר הוא פרמטר שהגיע אליו ולא יודעת אותו. מאפיין את המשפחה של הקולגיות שלו. תוחלת, זה לפעמים הפרמטר. הפרמטר זה, כשאתה מדברת על, אני יודע, התפלגות מסוימת, נניח, מה ההתפלגות החביבה עליי? התפלגות פרמטרים, כשהכי אני יודע את המקרה הזה של ברנולי, או של, לא יודע מה, של נורמלי, לא יודע, או פרסום, x given תטא יהיה, אני יודע, תטא e במינוס חלקי תטא, או משהו כאלה, חלקי תטא. זה נורמלי. תטא פה במקרה הוא גם הממוצע, אבל זה לא חייב להיות. ממש לא. אם הייתי כותב תטא בריבוע, זהו, התוחלת של x, התוחלת של x היא תכונה של פרמטר. התוחלת של x היא מקרה הזה שווה לתטא. אבל זה לא חייב להיות. הממוצע זה זה. הוא פונקציה של המדגם. הוא תמיד פונקציה של המדגם, כן, זה שאלה. נכון, נכון. הסטטיסטי הוא תמיד פונקציה של המדגם, אני הייתי צריך להגיד את זה יותר ברור, זה לא לך או לא טוב. לא, את כמעט לא הבנתי את אף אחד לעניין זה. פשוט מאוד. זאת אומרת, זה חשוב מאוד להבין אני לכן מצייר כל הזמן את הדיאגרמה הזאת. למה מצייר את הדיאגרמה הזאת? בשביל להדגיש שוב שהפרמטר, המדגם נוצר, כאן אני דוגם. IID דוגם את התפלגות הפרמטר, מקבל מדגם. אני לא יודע מה הפרמטר. עכשיו אני מחשב מתוך הפרמטר סטטיסטי. הוא פונקציה רק של המדגם. זאת המשמעות של החצים האלה. הוא לא מכיר את זה, הוא מכיר רק את המדגם. ועכשיו אני רוצה לקשור את זה חברה לתכונות של הפרמטר. אם זה למשל, בגלל אני מייצר זאת אומרת, כמו שראינו, הוא הולך להיות פונקציה, עכשיו איזושהי פונקציה, כרגע, איזושהי פונקציה. כל הרעיון הוא שהפרמטר לא תלוי, האסטימטור לא תלוי בתטא, כי אם היה תלוי בתטא, אז אני מעריך אותו בתוך המדגם. אז כל הדברים שאני רואה סטטיסטיים הם פונקציות של המדגם, לא של הפרמטר. עכשיו, מה שאומרת לי הפקטוריזציה הזאת, שזה אולי באמת היה קצת מאוד אבסטרקטי. אני אומר שאם את יכולה לפרק את ההתפלגות הזאת לפונקציה של המדגם, שלא תהיה הפרמטר, כפול פונקציה אחרת של הסטטיסטים ושל הפרמטר, אז ורק אז זה מנסה את כל האינפורמציה. אני אראה לך שכל עומד, לפחות העומדים הטובים, תטא מקסימום לייקליות ותטא מקסימום פוסטריורי ותטא L2, כל הדברים האלה וכן הלאה, כולם פונקציות של הסטטיסטי בלבד. לא, כולם ינבעו על זה שתקחי את הלוג לייקליות ותגזרי לי לפי משהו, לפי הפרמטר, זה בלתי תלוי במדגם, אלא דרך הסטטיסטי. ולכן הסטטיסטים כל כך חשובים מבחינתם. הוא מספיק, כל מה שרציתי לדעת על הפרמטר נמצא בסטטיסטי. אני רוצה להגיד את זה בעוד דרך, זה נורא חשוב מה שאמרת עכשיו, אז אני חייב להגיד את זה לכולם. השאלה הזאת היא שאלה שאומרת לי משהו מאוד פשוט במובן. לא, אבל שאלה חשובה מאוד, היא שאלה חשובה מאוד. אני אגיד את זה עוד פעם, אני היום מרגיש שזה קצת מוזר ואני לא לגמרי קוהרנטי, אני יודע, אבל בסדר. טוב, מתי? So please, so I got one important question from Karen, as usual, during the break that showed me that maybe I'm completely off as far as. So again, the reason I always show this chain, this Markov chain, there's a parameter. You don't know the parameter. You sample your distribution. You get a sample. All you get are numbers of samples. And then you calculate the statistics from the sample, which means it's not aware of the parameter at all. And from that, we are trying to estimate the parameter again from the statistics. So the estimator and the statistics are not functions of the parameter. They are not directly depending on the parameter. They depend only on the parameter through the sample. They are functions of the sample only. And essentially what I said is that all the good estimators, like it's obvious for maximum likelihood and for maximum posteriori, because then you take derivative of the log likelihood one way or another. And it's also true for other type of estimators, not all of them, but for example, the L-square or the MSE or the minimum. Most of them, because of this factorization, when you take the log and take derivative with respect to the parameter, it will depend on the sample only through the statistic. And that's really the important property. The statistic is a function of the sample. That's why you can calculate it from data and estimate the parameter from it. All right, so I don't know. This should be clear to everyone. Now, I'm going to do something which is different from what I did in the past years, and definitely from what Amir was doing in the course. But we see that somehow the information theoretic functions creep in slowly without. So, for example, I want to do some introduction of some functions of information theory at that level, mainly as definitions, and later on we'll see several what we call coding theorems, which really make these functions so important. I mean, why are those functions relevant? So we already defined the cross entropy of two distributions very early in the course. I hope all of you remember what it was. So this was the expectation with respect to P of the log probability ratio. Okay? And this was, and we proved that there's something which is sometimes called the information inequality. Sometimes it's called Gibbs inequality, because it actually goes all the way to Gibbs, although in a very strange way, but he actually was well aware of it in his derivation of statistical physics. So this is always positive, not negative, and it's 0 if and only if the two distributions are equal almost everywhere. Now, anything which contributes to the integral. And we call this the Kullback-Leibler divergence, the KL divergence. And we showed that it's not usually not symmetric. Of course, it's not symmetric. It depends. So this is, if you want, is a sum for discrete cases over all possible x's of this log. So there's a big difference between P and Q in this expression. P has a P log P inside, and Q has a Q inside. We already saw several things which are interesting in statistics with respect to this KL. For example, we showed that the theta maximum likelihood is the projection over all possible theta of the data. So this was the empirical distribution. So this is the sample distribution. Remember what it was. It's a distribution made out of histograms of the data, or the distribution which is made out of delta functions of unit mass on all the samples with respect to my parameter space. So this was the definition of maximum likelihood. And it's a special type of projection, and I'm going to elaborate on this later on. And somebody asked me, I don't remember who exactly, David or someone, asked me about why I don't do it the other way around. I mean, minimize with respect to the first argument. It's a very different thing. Minimizing with respect to the first argument is going to give you an exponential form, and this actually is very important. This is going to be related to something we call maximum entropy distribution and so on. So this is, without exaggeration, is the most important function in what we call information measures. It's extremely useful. I mean, it comes everywhere simply because log likelihood ratio is so important. Now, I want to extend it just slightly. First of all, I want to show two important properties of D, which we didn't show so far. One of them is what we call the chain rule. So the chain rule for D is the following. So let's say that I have two variables, x and y. And and I have two possible distributions of x and y, pxy, qxy. So I want to see what is the difference, or what is this divergence, or this relative. We also call it relative entropy. Relative entropy. Sometimes it's called information divergence. It has all sorts of names. Relative entropy, cross entropy. You find in the literature tens of different names for this quantity, because it comes all the way from many different places. In statistical physics, by the way, usually what we put here is the Gibbs distribution, and then it's actually directly related to what we call the free energy. Because if you put Q as e to the minus beta e, normalized, you get entropy plus average energy, and with a minus sign, and you get it exactly the Gibbs free energy. So this is, again, a very important function wherever you look at it. Now, the first thing I want to show about this is that this is actually, and the proof is almost immediate, it's actually break into two pieces. So I just write what it is. It's the average with respect to pxy of the log ratio of pxy over qxy. But now, of course, I can break the joint distribution into a product of the marginal over x and the conditional. So this is simply this expectation over the joint pxy of log px over qx plus log py given x over qy given x. Why is this true? What did I do here? Yeah, so I just want to remind you that the joint distribution is p of x, p of y given x. This is always true. And of course, it's also p of y, p of x given y. I can always factorize it that way. I mean, this is simply the definition of the conditional distribution. Okay. So, but now this average, of course, is independent of y. So this is what? It's the d of px qx plus what? Plus the average over y over x, in this case, of the KL between py given x. So it's the average over y over x, p of x given y, of log px given y, py given x, px and y, sorry. Px and y of p of y given x over q of y given x. And this is precisely what we call the conditional KL. This is what it calls for. So if you can think about it again, I average over y given x, and then average over x. Average first on I factorize it like this. Take the first average is just the DKL for a given x. So if you want, it's the average over x over p of x of the d py given x qy given x. Okay, and this is what we call the conditional d. So we get something which we usually call the chain rule. And you can easily generalize it to more than just two variables. You have k variables. You just bring they can be dependent any way you want. So you can always break it into a product by conditioning all over the place. And if it's a Markov chain, it's getting much simpler, because so the general expression of this form will actually look like a long sum. So the general chain rule, not only for 2, but for n, will have this property. So if you have x1, x2 to xn, and you have some joint distribution of them, which is the assumption we always make. So this can always be written as px1 times px2 given x1 times px3 given x1 and x2, and so on. Okay? Up to the last one, conditional on all the others. Okay, so it's a long product. And if I just plug this into the KL, so the KL of two distribution of long process, a long sample like this, how will it break? So it will break in exactly the same way. It will be the KL between the first ones plus the conditional over the first average. So this is something which I can call KL of px2 given x1, qx2 given x1, averaged over x1, and so on. So you can easily generalize. Okay, so this is called the chain rule, and it's actually, in the case of independent x and y, what will it be? This is just the sum of the two KLs. Okay? Because then the condition of y over x is precisely the same as p of y. Okay? So this KL is additive for independent variables. Both as long as they're independent for both p and q. Okay? So that's not necessarily the case, of course. I mean, p and q can have entirely different distributions. Okay, so actually, so there are two functions that I must define, although I hesitate to do this. So this, again, it's a very non-orthodox way. So if x is finite, a finite random variable, which means it has only a finite number of discrete options, like die or whatever. Then we can define something which we call the entropy of x. Now this name is really an unfortunate historical problem, because entropy has different meanings in different contexts, and many of you here encountered entropy in physics or in chemistry or in other places, and it's actually coming from an entirely different place. But for our purpose, the entropy of a variable x, a discrete variable x, is simply defined as, I can define it as the DKL as minus sum over x. Remember, this is a finite sum, p of x log p of x. This is a very problematic function. I really want you to deal with it with great care, and we'll show later on, of course, that this is on its own is very important, and it has a very nice meaning as some sort of uncertainty measure or missing information or whatever you want to call it. And of course, it will be really important when we prove that this is a lower bound on compression and so on in the coding theorem. But at this point, how is it related to cross entropy? The cross entropy is a much better defined function. I mean, this is why I emphasize it. This is the fundamental thing as far as I'm concerned, because this is defined whether x is continuous or discrete, finite or infinite, doesn't matter. This is well defined. It's always positive. It's always well behaved. Of course, it can be infinite if q has a smaller support than p, and so on and so forth, as you saw already. But age, I cannot even say that in general this is a non-negative quantity unless it's a finite discrete variable, and then it is. But how is it related to the KL? So I can think about it as log of the cardinality of my state space, of my space which was finite. So x is finite means that this is a finite number. So it's log minus the KL of P, and what? Something which we want to call the uniform distribution over X. So this is the way to think about it. It's essentially measuring the distance between the distribution and the uniform distribution. And this is going to be maximized when? When P equals the uniform distribution, because then D is going to be 0. Okay, so you already see from that definition, it's obvious that because the entropy of the uniform distribution is just log with the cardinality, and it's going to be the maximum possible entropy of any finite distribution, because the minimum possible KL is 0, where P equals the uniform. Okay. So think about this as my definition of entropy. But it has so many other interesting properties. In particular, it has, following from the chain rule of the DKL, you can show that the entropy of two variables, just following from my definition of my simple statement about the chain rule of the DKL, this is what? So this is going to be the entropy of the first one plus the entropy of the conditional, and of course also the other way around, the entropy of the second one plus the entropy of the conditional in the other direction. Where this conditional is the average conditional entropy, which means it's already here in this averaging. So I condition over X, and then average my entropies over all possible X's. So this is what we call the chain rule, the simple chain rule for entropy. Now this has such a fundamental importance because if you don't see it immediately, how it follows from this, simply use my definition, uniform here, and for any finite variable, this is obvious. It's actually true also for continuous variables, but you have to be very careful. What do you mean by the definition of entropy? Because so this is something I want you actually to show, and it's a very simple. If I really so entropy in some sense is an uncertainty measure. In a sense, it will make very, very clear later on. It measures the uncertainty in X. And for any discrete variable, it is 0. When will it be 0? So for discrete variables, it is indeed non-negative. And it will be 0 when? Yeah, if and only if, in this case, all the mass is centered on one value of X. You can see it immediately just from the definition I gave. But you can also look at it. I mean, any other thing will have non-positive. Actually, for two variables, the entropy of just a binary variable is something you all have to know. As I said, we'll see it later on in a much more interesting context of coding and compression. But at this point, so if you just look at the binary entropy, so X is 0 or 1. So sometimes we write this with a small h, but never mind. I write it h of X in this case is simply P log P. And in this case, it's actually useful to take the base 2 log minus 1 minus P log 1 minus P. And this is just so this probability, where P is the probability of X equal, and the probability of X equal 1, let's say. Probability of X equals 0, and 1 minus P is the probability of X equal 1. Okay? So how does this function look like? So you all have to remember this. So if this is my P, P, this is completely symmetric with respect to P equal 1/2. Okay? So whatever it does up to 1/2, it will do the opposite on the other side. And it has a maximum precisely at 1/2. And if I take the log to the base 2, then we actually say that the entropy is measured by what we call bits, or binary units of information. So then this will be 1. So it has this particular shape. It has to be symmetric with respect to 0, to 1/2. My picture is not perfect. Okay, this is 1/2, and it's 1 for 1/2. Okay, and by the way, it looks very much like a parabola, but it's not a parabola. It actually has an infinite slope, as you can easily see, both at 0 and 1. Okay? So this P. So this is the example of the binary entropy. It has this symmetry with respect to P and 1 minus P, and it has a maximum at 1/2. And the maximum is just 1, or log 2 if you want in general. So this may be, all right, log 2, I'm not committing myself to anything. Okay, so this is an important function. Why is it such an important function? We already saw in the exercise I gave you in calculating the binary, approximating the binomial distribution, if you remember. If you don't, I'll show it to you at some other point soon. So the chain rule is actually very, very interesting. It tells us that the uncertainty of two distributions, of two variables, is the uncertainty of one if you really accept this name, uncertainty in X. It has this nice property, which actually Shannon took as an axiom, as a property that he required a measure of uncertainty to obey, that if you reveal the uncertainty in two variables step by step, first the first one and then the conditional one, the uncertainty sums. It's additive. Essentially, all it does, because you take the log of a product, and the product breaks into sum, and you get immediately that it's really up to some very trivial technical conditions, the only function which will do that for any distribution. And this is something you can take as an axiom, but I don't want to do it now. All right. So this is entropy. And as I said, it's an extremely important function. And I just sneak it here just because I want you to recognize it. And we'll come later on to the coding theorem and show why is it so important. And we'll also see why it's important in other domains like physics or statistical mechanics and many other places, and of course communication theory. But it's first of all important for us in the concept of decision making and hypothesis testing, simply because it's a special case of the binary, of the KL divergence. But okay, we'll come back to that. It's the KL divergence with respect to the uniform distribution. Now, there's another function I want to define, which is even more important than the entropy. And this is called the mutual information. So this function, it's really, I can't exaggerate its importance, but it's again, we are just starting to recognize it, and at this point, it's also one of the functions that on which there are so many misconceptions, there's so much confusion. It's really quite amazing. I mean, how many people write papers in Science and Nature, not to say books, without really about this function without really understanding it, using this function for all sorts of wrong reasons. So actually, what I want to call mutual information is trying to capture, in some sense, the uncertainty of what information one variable is telling me about the other one. So what would you take it, just this intuitive definition? Usually what we do here is using some sort of a Venn diagram, which is actually quite interesting. If you have two variables, x and y, and I think about the area of this circle as the entropy of H, how much uncertainty I have in x, and the area of this circle is how much uncertainty I have in y. So essentially, just intuitively, completely intuitively, you can get from this Venn diagram several quantities which are interesting. For example, how many uncertainty is left in x if I know y? So what should it be if this makes sense? So it should be really, so age of x is the whole thing. Let's be more concrete about it. Age of x is all this circle, and age of y is all this circle. So I just want to be more careful here. So if this is really, if the area is somehow a measure of uncertainty, we can justify it rigorously. Why is it? So the remaining should be this, okay? This is the uncertainty left in x if I know y. So this area should be age of x given y, okay? And this area should be what? The uncertainty. So the first variable was x, the second variable was y. I know it's a bit confusing. So this is the area, the uncertainty of y left in x. So what is this thing? This is exactly what I would like to call the uncertainty of both of them together, or the information that y gave me about x, or the information that x gave me about y. Now I know that at this point it looks just like a funny drawing that's supposed to help us. Actually, there is a fundamental truth in such Venn diagrams, which we can prove later on. But if this is true, then what is the uncertainty in both x and y? It's just the total area. Okay, the total area. So even without defining mutual information, you already see that this helps you remembering all the equalities we wrote down there. So the uncertainty in both x and y should be this. This circle plus what's left over, which is this hx plus hy given x, or this circle plus this leftover, which is exactly hy plus hx given y. So you see that these two, this equality, which I just proved from the chain rule of the KL, is actually very nicely captured by these two areas here. So, and of course, here's another way of saying it. The total area age of x, y is what? So it's age of x plus age of y. But there's something I counted twice here. The intersection. Okay, so it's going to be age of x plus age of y. It's going to be exactly that if they're independent. If the sum simply, but if there is some dependence between them, there should be something else. I should subtract something, and this something is precisely what we call the mutual information. So actually, this area right here, just from this Venn diagram, it should be, like, I want to call it IXY, and this is the definition, if you want, is simply the uncertainty in both age x and age y as if they're independent, minus the real uncertainty of both of them together. And much better definition is simply the KL between the joint distribution and the product of the margins. Okay. So this is my definition of the mutual information. The motivation is precisely to capture this area here. So what is it? Again, let's just make it more explicit. It's the expectation with respect to the joint distribution of the log ratio Pxy over Px Py. Okay, so this is our definition of something which you want to call the mutual information. Mutual information of x and y. Now, the reason I think this is more fundamental than entropy is, first of all, it's well defined. I mean, is this always positive? Of course it is, because it's KL divergence, so this is non-negative. It's non-negative whenever the KL divergence is defined, so continuous variables doesn't matter, I mean, it can be anything. And it has this very nice interpretation as when is it zero? If and only if the product is, the joint distribution is simply the product, which means if and only if they're independent. Okay? So later on, and I really can't emphasize it too strongly, this definition is nice, but it's nothing more than a definition. In order to actually make this useful, I have to connect it with some real properties that are important for us, like the decision time, or like the compression or error or whatever, some properties that we call physical properties. I mean, otherwise it's just a function of distribution which can be arbitrary. And of course, people indeed argued about whether this is the only way of measuring information or not. So I call it mutual information simply because this is how it's called, but I really didn't yet completely convince you this is anything to do with the intuitive notion of information. I actually argue very strongly that it's the only meaningful way of defining quantitative information, but we'll see later on why. We already know a little bit about it from the decision-making problem. So, yes?
Just about the thing being well-defined. So you're saying I is well-defined because it's been writing in terms of PKF, but the entropy might not be well-defined for continuous variables and so on.
Yes.
So, but it's just some.
Yeah, so whenever you write it like this, you'll have to make sure that you know what you're doing. These two functions are well-defined. Luckily, it's always a difference of entropy. So I can actually very easily show you just by looking at this Venn diagram. So you can write IXY in at least 3 different ways, which is almost trivial. I mean, essentially, so for example, I can write it as I just did. I mean, HX plus HY minus HXY. But I also write it as HX minus what? Minus H x given y. This has a very nice intuitive interpretation. It's the uncertainty left in x after I see y. I'm sorry. It's precisely this is the uncertainty left in x after I see y, and this is what was not captured by y when I about x. Okay, so it's the relevant information if you want. That's the way I like to think about it. It's how much y is telling you about x, and of course, because of the symmetry, this is completely symmetric with respect to x and y, as it's written here. It's also age of y minus age of y given x. Notice, by the way, that x and y can be entirely different. I mean, here I actually drew them more or less the same size, but this can have a much larger entropy than this, and so on. They can be very, very different. So the symmetry is somewhat surprising. The information that x contains about y is the same as the information that y contains about x. Now, later on, we'll relate this entropy to what we call yes-no questions and the question recording. So essentially, we'll show you that the entropy is the minimal number of yes-no questions that you need to ask in order to reveal the identity of a variable. And actually, the easiest way to think about it is something like the 20-question game that you all may be familiar with. I have a number between 1 and 100, and I want you to guess it. And I want to ask the minimal number of yes-no questions. So how would you do it? I mean, all of you saw it somewhere, especially all the computer scientists here. How would you do it? Yeah, so of course, a bad question is a question like, is it 17? Why is it a bad question? It's not a very clever question anyway, because you know, unless you really have a strong bias to 17, some people have. Usually, the probability that you get an answer yes is 1 over 100. Okay, so what is a good question is a question for which the answer is as far as possible from certain, which means half and half. It's the best question you can ask, and we'll prove this later on. What is a question half and half? For example, is it an even number? It's a good question. Or is it greater than 50? It's a good question, because in that cases, all the information is, I don't know the answer in the maximal possible way, in the sense that the uncertainty of my answer, which is this binary entropy, is maximized. Later on, we'll see that just this chain rule is really showing us that this is the asking binary questions which are as close as possible to even, to half-half, are really the best strategy you can get, and this will be the shortest questionnaire, or the shortest possible, the best algorithm for finding the number based on binary questions. So this is really already the beginning of properties of entropy, which will come out later. So here are 3 different ways of writing it. And of course, this corresponds to the KL between Px given y over Px. And this should, I'm sorry, Px given y with respect to Px. And remember what this is? So this is the posterior to prior uncertainty. Remember, you saw it already. I mean, so what you know after you see y with respect to what you had before you see y. And of course, averaged over y eventually. And this will be just the average D between Py given X respect to Py. And then I think that are so nicely related, but then that's average over X at the end. And of course, this is just how much uncertainty is actually removed if you know the joint of them with respect to the independence. All right, very nice. We come back, as I said, I mean, this layer by layer we'll discover more and more interesting properties of these functions. But at this point, I want just one interesting fact that I actually left for Noga to show you, which is called the data processing inequality. Again, so it's so important that in information theory we usually just denote it by DPI. DPI is data processing inequality. And again, I cannot exaggerate the importance of this thing for neural computation, or computation in neuroscience. Why? Okay, so what is data processing inequality? What would you like to happen? So if you have a Markov chain, let's say y depends only on x, and z depends only on y. So this is what we call, again, a Markov chain of the type that we show all the time. For example, this is the parameter, this is the sample, and this is the statistic, or things like this. Okay. So for a Markov chain, what would you like? I mean, so yes, in some sense, y is some sort of information processing, data processing of x. For example, it's just summing it or doing some processing to it. Okay. And z is some information processing of y. Again, in the context of neural network, think about it as what happens from one layer to the next layer to the next layer and to the next layer. Each layer is just processing the information in the previous one. So what would you like, if this information measure makes any sense, then what is the intuitive property you would like to have? Maybe I wonder how many of you can, who don't know it, can guess it. Okay, this ideally. I mean, this is no, you don't want them to sum. So I'm processing data. I'm taking, let's say, an image, and then calculate some features of the image, and then ask if there is a face or no face there. I mean, this is what, let's say, neural networks like to do. And you take the pixels of an image, you do some calculations, calculate some features, as we call them, some functions of the pixels. Usually, it's already reducing information. I lose a lot by doing this. And then I ask, eventually I want to say yes or no to the question, is there a face or no in the image? Or is there a car in the image? Or is there a house in the image? Or whatever it is. This is exactly the type of data processing that we do in our brain all the time. So essentially, we lose information. We only throw away information in this level. So what is really the intuitive thing that if really this is the right thing to work with, it should obey the following thing. And the following thing is precisely that. So the information